Hello and welcome to our webinar on torque rheometry vinyl testing with a focus on mixer tests today. My name is Matthias Jährling and I'm the Senior Application Manager here in our application laboratories in Karlsruhe, Germany. Today's webinar I will explain how to use mixers, will explain the basics to things you have to take care for to get good reproducible results. And I will show you how to discuss the results, to discuss the measuring curves, to see the point of interest also later on for the production. But before I start with the bits and pieces, I give you an introduction into the basic idea of torque rheometers. So first of all, the question is, why should I use such a torque rheometer? There are other test methods available on the market. What's the reason why especially a torque rheometer is good if it comes for polyvinyl chloride for PVC testing? Well, our materials are processed in a liquid molten state. And the viscosity of our materials and the change of viscosity will have a direct influence on its processing behavior. The torque rheometer simulates what's happening in production, and this way we can find the differences of the material more closer than other testing methods. Especially with PVC, where you need shear and pressure and actually an extrusion process to bring it into a molten state. So typically, who is using such torque rheometers? Well, of course, if you look from the material side, it is when you develop a polymer, when you develop a new compound formulation, but also if you want to check the quality of your compound, so incoming quality control or outgoing quality control. Another area where torque rheometers are used are in the development of a process. So designing machine and designing screw configurations and process conditions. A torque rheometer is a measuring platform. A platform that consists of a drive unit, and to this drive unit you can attach laboratory mixers, laboratory extruders, which could be single screw extruders or twin screw extruders. To this you can then attach different screws or dies to give it different shape, so to simulate the production process. The idea of a torque rheometer is not brand new. So here we see historical models on the left side. Here, this is a Rheocord M model from the 1970s. You clearly can see at the back the drive, and in front attached you have a laboratory mixer. In between you see a kind of a lever, a so-called dynamometer, which measures kind of the displacement of the gearbox if a torque is produced by a sample in the mixer. This testing method was changed then later on using strain gauge technology. So you see here on the right upper side for first electronical torque rheometer, and at the bottom here this is a torque rheometer from the 90s. That's how the machines looked like when I started to do our work in the lab. Nowadays this looks much more modern. Here we have a floor standing model, our PolyLab OS, and there you can drive different measuring accessories in front of the machine to connect, and at this stage here we have this laboratory mixer. Let's have a closer look to laboratory mixers. A laboratory mixer is made from 3 segments. You have a back plate, there you have bushings inside where the rotors are attached. In the middle chamber, that's actually where your material gets in contact with the chamber most, and there you have also the rotors for the testing of PVC dry blends or PVC. You normally go for so-called roller rotors. And then, of course, in the front, you have a front plate, a heated front plate to close the system. The rotors inside of the mixer are counter-rotating, and they rotate in a gear ratio to get a good distribution, a good mixing effect. What you measure during a test is the torque, so the force you need to run those rotors, and the temperature of your sample inside of the mixer. From the torque, if you summarize the torque, you can then also calculate the energy you put into the sample. If we display these values, the torque, the temperature, and the energy against the time, we get a so-called mixer rheogram. So here we see a typical mixer rheogram of the fusion of a PVC dry blend. The test starts with a significant increase of the torque. That's the blue line where it rises in the beginning. That's when I force in my PVC sample, my PVC powder, into the running mixer. Now the powder is distributing inside of the mixer chamber. Some additives like waxes, processing aids are already melting. Therefore, the torque goes down, comes down to a minimum, and then starts rising again. What happens here is that the material starts to agglomerate and starts to build up areas of molten or fused material. And that continues with an increase in viscosity until it comes to a maximum. This is our second peak in the curve, and this is where we have a fully developed melt of a fused material. Now, due to additional shear we put into a sample, because the rotors are still running, the temperature is still rising until it comes to a steady state. And together with that, also our torque signal first goes down a bit and then comes to a steady state. You can say the torque at the end of this curve is a relative value of the melt viscosity of a sample. Very important for the people in production is the time. How long does it take to develop this melt, to have this second peak, this fusion peak? Because if this peak is shifting in time, so takes longer to melt, they will have this effect also in the production. If we have a look, we could actually say that what's happening in the mixer over time is what's happening in an extruder along the extruder screw. In the beginning, we have a significant rise in torque because now we force in our PVC material. It's cold, it's taken into the extruder. Now the powder is distributing inside of the screws. We will have a rise in torque on the screw again because now my material starts to melt, develop a melt. We have then the highest torque. Then due to further heat, viscosity of my compound comes down until we come into a certain degree of gelation. Here could be the end of my extruder, and here I could attach a die to shape it, to make a tube, a window profile, or whatsoever. And theoretically, if our extruder is too long, then something else happens with the PVC, and that's its degradation. That's what we can see at the end of the curve. I will talk about the degradation at the end of the webinar. Next, I'd like to show you the laboratory mixer we have in our lab. We have here our setup on a movable frame. On top, we have a pneumatic feeding device. Feeding devices, also manual feeding devices are available, but especially for PVC, where the reproducibility is so important, I would also recommend to go for a pneumatic feeding device. So let's go up with the piston and open the safety guard. Here we have the loading chute. This is a round loading chute. A round shape helps us to keep it more sealed, and we have a bit higher volume we can use to feed materials. The mixer itself is made from 3 segments. The first plate has a safety chain. The moment I remove the safety chain, the motor will stop, and this way I'm safe and not mixing my fingers. Here we now have the middle chamber. Inside you can see the rotors. And now we have the middle chamber and at the back. The rotors here are easily to exchange. There are other geometries of rotors available for mixing rubber materials or other polymers, but for PVC we usually stay with the roller rotors. So let's prepare everything for a measurement. For this, I place everything back. And now we will prepare the measurement on the software. To prepare a measurement with the software, we're using our Polysoft mixer software. This software module is designed especially to run mixer tests. The structure is that a supervisor can predefine a measurement, how it has to be done, and later on a lab person just has to press the start button and is then guided through the measurement to make sure he's working reproducible. So let's define such a measurement. First, we have to set up the machine so it automatically detects we have a mixer attached and, well, the roller rotors have been selected. So next step, we put in information on our sample. Here we put in, for documentation, sample numbers, material descriptions, important, the melt density, and also the mass we want to use, because from that value, later on, the specific mechanical energy is calculated. You can force a user to edit this upon start, or you can simply keep it pre-selected. Next step is now defining the measurement itself. Typically, a measurement with a mixer is just defined. You set a defined temperature, the steel temperature, the defined speed of your rotors, and a certain time you want to run this measurement. I think 5 minutes is enough for our material in this case. The software also allows you to program more sophisticated routines, like I can add additional points, like, for example, if the melt temperature is rising above 190 degrees, please cool down the mixer, and then you have that as next mixer step. But typically such trials just go for one step. So we've predefined the measurement. The next point, I can now decide how the data will be evaluated. So here I can use predefined evaluation routines. You look for a curve that fits to your measurement. So we have here one for the PVC melting, for the fusion for PVC. If you want to see more detailed what's behind that, so we can see behind this routine here, the calculation is that we look for the start point, the first maximum, the loading maximum, then the minimum of your curve. Then we look for the point of inflection where the curve is changing its direction. Up it goes to the fusion maximum and then later on to the minimum. And if I activate that, this routine will automatically be calculating the data after the test is finished. The next step of the job is how the data is saved, select the name, and also it can be decided if it should be exported into other formats like Excel or so. So definition of our test is done. So the next thing I have to do, or the lab person has to do, is to start the measurement. Now computer is checking if temperature is reached and gives me a warning. We will do now a calibration, so to zero out all possible torque coming from the rotors. Now machine is running and it tells me to fill in 68 grams of material. So first lift up the piston, go for the sample, press the material in, and now the measurement has started automatically. The software detects a rise in torque, and for the software this is the signal to start the measurement. If we now look at the curve, we see how the torque is going down. PVC powder is distributing in the mixer chamber. Now we can see that due to the shear and the heat inside of the mixer, PVC now starts to agglomerate, building areas of more fused material, which results in an increase of viscosity of my mix, and this we can see here in the rise of the torque. After a while we do see that the torque gets constant, so we come in kind of a steady state, and this torque now shows the relative viscosity of our compound. After the test time has finished, the mixer will stop and will now automatically calculate the points of interest at our curve. So we can see here it looked for the beginning of our trial, looked for the first maximum, well, the minimum. We see here the point of inflection in the increase of torque. Here the curve changes direction back to come down to an end. The software now looks for the maximum of this curve, but we also see here two additional lines. In older times, the people with the analog printout simply used a ruler to make a straight line here and a straight line there to look for this crossover point. Such a point was much, or is still much, easier to reproduce than searching a maximum on a curve. Even for software, this crossover point is much more reproducible to calculate. But before we go into more details about this curve, I will have to clean the mixer to avoid degradation. The cleaning of the mixer with PVC is quite easy because the material does not stick to the metal. For that now I raise up the piston, remove the loading chute, remove the safety chain. Now drive is disabled. And now let's open the chamber. So we can now brush away the material. To clean the mixer chamber, you have two additional buttons at the side. If you press them at the same time, this mixer rotors will rotate in a low speed, and this makes it more easy to remove the middle chamber, and also it helps to clean the mixer. Oh, actually the material simply falls off. Now let's have a closer look to the results we did get from our test. If you look here at the top, you see a variety of tests. I did some pre-tests already to show, first of all, the reproducibility of the sample. So I can select other trials to compare the data. So you can see here 4 measurements overlaid. You can also see now the fusion peak here is not so well reproducible, but this crossover point is always very nicely reproducible. From that measurements, we can see the test is very well reproducible if you make sure that the user is working reproducible. In this trial, I also tried to do some mistakes, some purposely wrong settings. So for example, changing the rotor speed from one test to the other. Of course, this results in differences in our test. You can see that the curve we did with a lower rotor speed takes longer to melt. Well, this is not so common to make wrong. More common is, for example, if you don't wait for steady state for the mixer temperature to come. So what you see here are differences in the temperature because I didn't wait long enough to get the mixer back to steady state. And this is resulting significantly in different melting behavior. You have to keep in mind these two curves show exactly the same material. So it is important to wait until the mixer is back to the set temperature. And also a very significant influence is the weight of your sample you put into the mixer. The thing we see here is a difference of 2 grams. So this means here we have had our 68 gram. This was the reproducible curve. And the other curve shows the same material. The only difference is 2 grams on the balance. So again, a significant difference between these curves. So this should show how sensitive the mixer is to changes. Well, it's good because we want to see those changes in the samples as well. But we also must be aware that we have to be reproducible to get reproducible results. And I'd like to show you another example. Again, just the curves. What we see already here, 10% mistake or difference on the balance does result significantly on the fusion behavior. And I like this example because when you open the mixer, you see really the difference. So this is 60 gram, this is 66 gram. It is the same material. The only difference is the change of the sample weight in the balance. Again, this should show how important it is to make sure you are reproducible. Now, in the beginning of the webinar, I've also talked about the PVC degradation or mentioned the PVC degradation. So let's have a closer look to that now. If we look at a typical curve, so the first section here, this shows the test we just did. We looked for the fusion behavior of the sample. If we prolong now our mixer tests for longer time, at a certain point, we will see that the torque will go up again. In this torque increase is due to the cross-linking of my PVC, which goes along with its degradation. If we look at PVC, we actually cannot process it without adding stabilizers. The moment you heat PVC above a certain temperature, it starts to degrade, which means that chlorine ions are developed, and these chlorine ions causing an autocatalytic effect, so boosting the chlorine production, so you have a very fast degradation. To avoid the degradation and make PVC processable, you have to add stabilizers that catch these chlorine ions and take these ions out of the system. But these additives, these stabilizers, have a certain capacity. After a while, they are saturated and not able anymore to stabilize the PVC. And that's what we see here at the end of the curve. Here, our stabilizers are saturated, and now the PVC degradation starts. You don't want to have this degradation in your production machine. Here, HCl is produced. Here, the material turns from a easy to clean material to a nasty, sticky, corrosive black mass, which can even pollute the next extrusion. So you really don't want this to happen in production. Therefore, also the stability test is very common. Now let's have a look how sensitive the test is to check for this stability. Here we see now an overlay of two mixer tests. Both compounds are exactly the same. The only difference between these two compounds is the stabilizer content. One material has 0.1% less stabilizer, the red curve. So what we can see, if we look at the end of the curve, the higher stabilizer content results in a longer stability of our compound. Well, we expected that. The other thing we can see, the viscosity of my compound is not affected by this change of formulation because the curves are here exactly the same. But if we look now in the beginning of the curve, we see a significant difference. So the higher amount of stabilizer has changed the fusion behavior. And this is something that must be avoided if you change a formulation. You try to make a formulation better by adding stabilizer, but on the other hand, you need longer time to melt the material. If you want to make sure that the people in production don't have problem with this new compound, you must change the whole formulation, maybe reduce the amount of lubricants to bring back the shape of the curve, of the green shape, to fit to the red curve. Only then this material will behave the same in the processing, in the extruder, in the production. So with this, I'm at the end of my webinar, and I'm now open for discussion and for your questions.